Welcome everyone for this third talk. Now I'm receiving Jonathan Boccara, who is a principal engineer lead at Murex in France. He works on large C++ code bases. So remember, Barney showed you some C++ code, and if you're not familiar with C++, well, Jonathan is working with that every day. I know Jonathan from we met in Paris because he's really involved in the software crafters community here. But also I was reading his blog. He's writing a lot about writing good C++ code. So his blog is called fluentcpp.com. If you're into C++, you might be interested in reading that. And recently he wrote a book called The Legacy Code Programmer's Toolbox. I read the book. It's really good. And I think the talk he will be giving today will show you a few glimpses of what are the golden gems that are inside his book, because he will be sharing 7 concrete techniques for you to approach legacy code. So with the previous talks, we have seen a few techniques like approval testing to get to legacy code under test and be able to refactor that. But Jonathan has much more approaches that you can try and use on your code base and see how it works. So without further ado, Jonathan, you're up.
Thanks, Nicholas. I think you've introduced my life as thoroughly as you could, and I don't have much to add about myself. So we're just going to move into the talk about 7 techniques to understand existing code, and in particular, legacy code. Why is that useful in the first place to be able to understand existing code? Well, if you think about why we want to do that, we can as well go back to why we do what we do. What it means to be a software developer. Well, to be a software developer means that you can write good code, obviously, but that you can also integrate this good code into existing code, even though all the existing code in the world is not as perfect as we would like it to be. So regardless of its quality, to do a good job, we need to understand existing code and to understand it pretty quickly, because there's a lot of it out there. And chances are there's a lot of it in your company as well. And the faster you can figure out how it works, the better, because the more time you save and the more good code you can write into your code base. So this is really the intention behind this talk. It's to go over 7 techniques to figure out code. Those are not the only 7 techniques in the world. There are 7 of those that use on an everyday basis, on a day-to-day basis, and that I find really useful, and that saved me a lot of time over the years. We're going to go to break that down into 2 parts. The first part is about exploring the code with a helicopter view, trying to figure out how things are connected, getting an overview without getting into the details. And the second part is about reading lines of codes and reading them quickly, just like you can quickly read a book and become a speed reader. We can also quickly read code and become a speed reader of code. Let's move on to the first part, exploring the code. And a good place to start is technique number 1, which is, I've put that first because that may be the one that saved me the most time of all. So what do I mean by the I/O frameworks? To understand that, let's see an example. Let's have a look at this piece of software with an inviting compute button and a text box next to it. So the user goes over the button, clicks the button, and there's some sort of calculations that's going on, and the answer is 42. You can imagine what the question is, but the answer is 42 in this particular case. Now, this this animation went extremely fast. It went extremely fast. If we do that again, but more slowly, just to make sure that we see everything that's happening. So let's do that again. The user brings the mouse over the button, clicks on it, and then something happens. We get into the code. The execution gets into the code. And what's remarkable about that is that when the user clicks on the button, there's this purple wormhole that drives the execution right to the right place in the code base. Even if the code is like tens of millions of lines long, this purple wormhole we went through drove us in a blink of an eye to the right part in the code that corresponds to that compute button. At the end of the code, there's a 42 that pops out and that gets brought back to the UI. Now, those wormhole are the UI framework. The UI framework, how to bring you from something that you can see with your eyes in the application over to the code that corresponds to that piece of software. So if you want to know, if you want to access some part of the code that that corresponds to something that you see in the application, the best way to reach it, if you don't know where it is to go through the UI. So technique number one is to get familiar with the code of the framework, which means that given any event, any UI event, like a click of a button, for example, you should be able to go all the way through the framework into the business code. In practice, it means that you set aside a couple of hours, one afternoon, for example, and you fire up the debugger and follow everything that's happening from the events all the way to the code. So that next time you want to find a piece of code, know where it is, you can do that in no time. This has saved me probably hundreds of hours of search in the code base. Now, the UI framework is relevant if your app has a UI, but if it doesn't, then it doesn't make a lot of sense. So perhaps you're building a service that just doesn't have UI but some interface, like a REST, for example, interface. Or perhaps what you're seeing from the application is just logs. Or perhaps what you're seeing is unit tests. It doesn't really matter. What matters is that you want to focus on what you can see from your human perspective, and find your way from that over to the code. And that's what I call the I/O framework in the general sense. So the I/O framework is our purple wormhole that brings us from what we see to the code. Now, what do you want to go and look for in the code? Imagine that you know your I/O framework and you can travel the purple wormhole. What are you going to look for? One thing to look for is technique number 2. It's a stronghold. So I'm not a native English speaker, and I learned the word stronghold in Game of Thrones. In Game of Thrones, a stronghold is a small castle, and there's a family that lives in the stronghold, and their people, and it's like their safe place. It's their base. And that's the position where they start everything when they go battle or make allies or whatever they do in Game of Thrones. But the stronghold is the base. It's the place they know very well. If you remember those games that we used to play when we were kids, at least when I was a kid, we used to play that. I don't know if they're still around. Those games, those strategy games where you have a fog of war that covers all the map except this place where you have your starting point. Remember those games. And then the more you explore and the more you embed in the fog of war, like Age of Empire, for example. Well, this is, I think, a great analogy with a code base, because you can think of the map as the entire code base, like the world is the entire code base, and the stronghold is the one piece of code that you understand perfectly well, that you feel safe with, even if it's small, right? The stronghold is just a small castle. It can be even just one line of code that you understand perfectly well. You know what this line does. You know why it's there. You know what it maps to in the application. You know this line of code perfectly well. The point is that if you know it well, chances are you can also understand the line before it and the line after it. And then you know 3 lines perfectly well. And then you can go one line before, one line after, and you know 5 lines. And little by little, the context surrounding those lines of code starts to make sense, and you can walk your way outwards to get a good understanding of a piece of code. One example of Stronghold that I used once is linear interpolation. So linear interpolation is this formula when you want to, you know what linear interpolation is, I guess. It's just a math formula. I'm comfortable with this formula, and I know a use case in my project where it's used, right? And in this example, I wanted to get more familiar with the code of one particular feature in the application, which I knew was performing a linear interpolation. So to understand that code, I went inside of the code, thanks to the IO framework, and I looked for the linear interpolation. I was looking for that one line of code that did the math formula. Once I found it, I could figure out the code surrounding it and work my way outwards to understand most of the code of the feature. So you can have several strongholds. You can have more than one, and the more you have, the better. And you can work your way from that stronghold and get a better understanding of the code and to understand more and more code of the code base. Now, a stronghold is something that's quite local, even though it's useful to get some understanding of a local piece of code. It's also interesting to be able to have a broader overview, like a helicopter view of the code base, or at least a part of the code base. I think one great way to do that is to analyze call stacks. So imagine a call stack that spans across several modules, right? I think it's a very interesting collection of information, because it shows you at runtime what are the connections between several modules, right? And I think that it shows how things are connected in the code base and how they're related together, how various modules relate together. One thing I often do with people of my team, the people that I coach in my team, is to sit with them and select a call stack that I know, and we put a breakpoint and we break in it, and I show them the call stack and we discuss the call stack. Right, and we have a look together at the various layers inside of the call stack, and we make sense of what's happening. Now, back to the map analogy, the call stack gives you a view spanning across several parts of the code base or several parts of the world. Now, this would be a good call stack, and that one would be not that good, because well, it is just a map, but you can imagine that the one on the right doesn't give you as much information as the one on the left does. So if we go back to the code, what's an interesting call stack? Well, there are, I think, two things that make a call stack interesting. The first one, obviously, is a deep stack, because the deeper, the more information it has. But there's also something else. I think what makes a stack very rich in terms of information is if it's in a common use case for your piece of software, right? Because if you're starting with a piece of software, you want to start to with the basics, with the most common thing that the software does, right? That's why you want to have a view of a call stack of the common use case. Now, how do you find them? Well, one way to do that is to ask around. If you have someone who's experienced on the project, then you can ask them. Right, come on then. Yeah, another way to find an interesting call stack, if you don't have someone experienced, because there are projects where you just don't have somebody who will tell you. Back in Paris, when we met with Nicholas, in this meetup, we heard stories. We heard stories of people inheriting from projects when they had no idea what was going on, and no one has no idea that people had left. So you still need to find your call stacks on your own. To do that, you can just ask for what use cases are common. You can ask the product people in your company. And if you don't have them, you can just ask customers why they like this piece of software, or if they don't like it, why they use it. And when you have the use case, you can work your way back to the call stacks by using the IO and ending up in the right code and setting breakpoint in that code. Right. So another aspect of call stacks is to see several ones at the same time. This is what flame graphs do. They will display they will sort of capture at runtime the various call stack that execution goes through and aggregate them together. That's a lot of information, but in some cases you can see something popping out and showing you interesting call stacks. So this was the first part of having a global overview of the code. Now let's recap. The first technique was to know your IO frameworks. The second one was to find a stronghold or several stronghold and work your way from them. And the third technique is to analyze call stacks like we've just seen. Now, at some point, you're going to have to read code. Right, you're going to have to sit down and have a function, for example, in front of you and just figure out what it does. This is what we do pretty much all day, particularly if you work with legacy code. So the faster, the better. How can we figure out what code does in little time? This is what we're going to see with 4 techniques to do that. With the analogy of speed readings with books, we can think of code like as prose. We can think of a function, for example, any piece of code, class, whatever. We can think of it as like a book, right? And there are techniques to figure out what a book is about and to capture the information in the book. And I think that those techniques, some of them at least, can be applied to code. So let's open the book and dive in. Well, there's this great book that's called How to Read a Book, which is about how to read a book, essentially. And it's like a classic. It's been a bestseller for like 100 years, something like that. And in this book, you can read about how to figure out what a book is about in very little time. Some takeaways that I got from that book are that you never want to read a book cover to cover, unless it's fiction. But I think code is more like non-fiction, unless you read code to have a good time. But if you're reading legacy code, maybe you're not reading it just to have a good time. So I guess we can make the analogy between code and non-fiction book. And non-fiction, you don't want to read it cover to cover, which means that code, you don't want to read code line by line, right? Which is something that's like I could never have guessed that if I didn't know it. Like when you start out as a developer, you want to read line by line and understand everything. Well, we shouldn't do that. We're going to go in more details into that in a moment. And the second thing is that your purpose is not to understand everything, right, from a book and from a piece of code. Right, there are some details you don't care about. If for example, if you just want to know what a function is about, what it's doing, because perhaps it's being called in a call sign that you care about, and you don't want to know everything about the call function, but you still want to get the general idea, then you don't want to understand everything in the called function. And the thing is the last thing is to focus on where the information is, right? If you can just go where the information is and skip everything else, then obviously you're going to go really fast. So our purpose is to adapt that to code. How can we, in a very concrete way, apply this advice and figure out code? Well, let's start with technique number 4, which consists in starting to read from the end. This is actually one technique to read a book, is to look at the end. And also at the beginning, but also at the end, which is not something that we do naturally. Now, if we think about why, it's because information tends to be at the beginning and the end. That's true for a book, that's true for a chapter, that's even true for a paragraph. There seems to be this pattern where information is like summed up at the beginning and the end, and in between is just details, right? So if we think about how this applies to code, if we think, for example, about how this applies to function, then the beginning is the prototype of the function, like the name, the return type, and the parameters. That makes sense, and that's what we would read in the first place in general. Now, what's more interesting is to think about what's the end of a function. What does that mean, the end of a function? Well, let's see an example. I'm going to show some code which I've taken from an open source repository on GitHub that happened to have the license that allowed me to show it on slides. It's not to pick on that particular project. I don't think it's particularly good or bad. It's just to have some code to discuss. So this is the code. Let's not read it line by line, like we said. Let's just start with the end. We know nothing about this code, and we'd like to figure out some information about what it's about. So let's start with the end. The end is a return statement. It returns alignments. I don't know what alignments is, but it looks like it's important in this context, because the purpose of all this code is to return alignments. Now, if alignments is like the main character of the story of the function, then the other things alignments interact with, or the things that contribute to building alignments, must be also important. So to build alignments, apparently we use block. So block must have some sort of importance. And to create block, we use reader, and to create reader, we use is. And before we know it, we have the structure of the second half of the function. We don't know what those names mean, but we know the structure, what is important and what contributes to what. This is just a starting point, but it takes very little investment to get. Now, the end, so it's the output in the function, like in a return statement. But return statements are just one way for a function to produce some outputs. There are other ways. For example, a function can produce its outputs through a parameter, like by filling a parameter. Or it can, if it's a class.
Oh, wait a second. We lose your sound. We don't have your mic anymore. Maybe try to change the input. Still no sound. So technical issues. Yeah, it happens. I don't know why the sound just suddenly stopped.
Again,
Oh,
can you hear me?
you're back. Yes.
You can hear me. Okay. Let's continue then. Right. So we're saying that we had several kind of outputs: return values, output parameters, data members. If it's a class method that changes the data in class, that can also be I/O, like printing something or changing something in the UI. All those are outputs from a function, and that's not just that. A function can also change a global variable. Or even worse, a function can return some information with an exception to hack an exceptions to return its output, which is disgusting. But the thing is, it happens. There is code out there that does all of those 6 ways to return value. The point is that all those count as outputs. So when you read a function from the end, it means that you want to look for the outputs, right, and work your way back from the outputs. And one place they often are is at the end, because the goal of the function is to produce the outputs. So most of the code of the function is like the prerequisite to do that. So you would expect the outputs to somehow appear at the end of the function. It's not always the case, but that's one way to one place to look for in priority. Now, can you find 100% of the outputs 100% of the time? Probably not, but you can find most of the outputs most of the time, and I think this is what we want to look for first in the function. Another place where the information is in words, in terms that occur frequently. Let's see an example. So we have this piece of code, still open source from another project on the internet. Don't look at it line by line, it's too small anyway. We're going to run a word count on this piece of code, as in for each symbol, each word in this piece of code, we're going to count it. We will go back in a moment about how you want to count words, what tools we have at our disposal to count words, but let's assume that we have a tool and it produces that. That means that the word len appears 20 times, the word value appears 17 times, the word C setting appears 15 times, and so on. It probably means that len and value and C setting are important in this function because it keeps talking about them. And indeed, if we look at one of them, like value, if we highlight value in the code, if we look at those places, those lines of code in particular, we can see a pattern. All the occurrences of value are places where we assign something to value. and it's all the way through the function, which suggests that one, value is important, and two, the purpose of the function is to fill value, right? And again, this is something that you get in a blink of an eye, as opposed to going line by line. If you read the code line by line, it probably takes like 2/3 of a function, like I don't know, like 50 lines of code, to figure out that value is important and that the function probably sets value. So getting a word count gives this information up front. Now, another interesting piece of information in this word count is the inputs of the function reg key and var name. You can see at the beginning, at the top of the screen, that reg key and var name are the parameters of this function, and they happen to be in the most frequently occurring words. In this table, there's not everything. I've truncated the table to the first 20-ish words. Yeah, the table goes down a long way. So reg key and var name are quite high. So they happen to appear a lot. And if we highlight them, we can see a pattern, right? We're not going to explore this pattern now, but the interesting point is that they seem to work together, right? Which is in itself a piece of information about those parameters and can contribute to their understanding, right? Or perhaps maybe some refactoring. If they belong together, perhaps we should group them in some sort of a structure. Well, it's not really the point. We're talking about understanding, but sometimes and quite often actually, understanding gives ideas for refactoring. This is not to say that inputs always appear frequently. Like, look at this piece of code, for example. This input appears only once, right? Now, another interesting statistics that we can get from a chunk of code is the span and the proportion of any words. So in this table, we've got two new columns, span and proportion. If we look at the first line in this table, items appears 11 times, as we can see in the second column, and it spans across 44 lines, which means that the distance between the first occurrence of items and the last occurrence of items is 44 lines. Now, it doesn't mean much if we don't know the total length of the function. And if we have it, then it's interesting to see the proportion of this span over the total length. Right, so proportion is span divided by total length. So those 44 lines represent 85% of the area of the function. Right, so items is quite present in the function. It's the highest. It's the most frequently occurring word, and it's all over the place. Good. Now, it's obviously something important in the function. Now, another pattern that we can see is something, I don't know if you see it, but there's something, there's one word that's one that looks special in this table. It's token. It looks special because it's the third frequent word, but at the same time, it has a very low proportion. If you see the proportion of the other ones, it's over 50, and this one is 29, which means that it's occurring frequently, but in a small span, which means that it's reduced to the scope. And indeed, if we highlight it, we can confirm that visually. Token is intensely used, but in a small subpart of the function, which suggests that this part of the function, the while loop here, is focused around token, right? So this is a starting piece of information to understand this first half of the function. Perhaps it's to set token or to read from token. We don't know at this point, but we know it's about token. So we want to follow token to understand this first part of the function. Now, like I told you, we were going back to how we can produce those word counts. One way to do that is by using rise. which works well if there are not too many lines. If there are just a couple of lines, then that's okay. You can have a visual impression of what word is coming up frequently. But if there are more than a few lines, it gets a bit too much. Obviously, we can highlight words one by one, or the one that we have feeling they would occur frequently by just highlighting them in the IDE. And the last tool is use an online tool. I couldn't find one to do just that for code, so I made one. You can find it on fluentcpp.com, which Nico was mentioning at the beginning. This is my blog. In fluentcpp.com/word count, you have a tool to paste your code in, and you get the word count. This is exactly what we saw on the slide. Now, how do we count words? Well, one way to count words is to count words, as in entire words, but we can also break up words in camel case to decide that perhaps some concept would appear in several names, even if with other words, and we can break them up. We can extract the various concepts in a camel case expression. So in this camel case expression, we would have words in camel case, and that would count as 4 different words. The tool can support that as well. And we can also ignore case, because perhaps in a camel case, we would have the same concept that appears at the beginning or the end, and you would not like to be sensitive to the case for that. Right, now we've been counting words on a function, but it's also interesting to count words on a wider span of code. For example, on a whole file. Like imagine, that's a true story, you have a file with just consonants in its name, and you have absolutely no idea what the name of the file means or what the file is about. So you can throw the whole file into the word count and have an idea of the most frequently occurring words, and it gives you a feel about what the file is about, right? This is really useful. Or you can count the words of a whole module, for example, a whole project, and then that's useful to get this overview. And if anything, that can bring up questions. For example, a new person joining the project can run a word count on the whole code and ask, I see that this word is appearing all the time. What does that mean? And start a conversation, and that would guide the person in its questions. Right, another place where the information tends to be is in control flow. By control flow, I mean all these little keywords, if, else, for, and so on, that are really the skeleton of a function. It's a bit like a table of contents, right? So back to the how to read a book. One of the first piece of advice that they gave is to have a very thorough read of the table of contents, right? Because the table of contents will let you know what the book is about and if you should read the book at all. So you want to spend time on that. Now, the control flow is sort of like a table of contents of a book because it gives you the main blocks, right? It's not perfect, but it gives you the main themes or some proxy of them. Let's try that on a piece of code. So this is a long piece of code that we're not going to read line by line, and we're going to run some filter that will only keep the lines that have control flow keyword in them. This is the vim command in case you're a vim user, but I'm sure you can get that in all IDEs, or you can collapse all the blocks with a small plus, for example, in Visual Studio, and so on. So anyway, in this code, the output is that, which is still not readable. I've chosen this example on purpose because the outcome was not readable. It often is readable, especially interesting for long functions that you can't really scroll your way through. By getting the control flow, you can know what it's about. But in this particular example, the outcome is still unreadable. But the thing is that this is still code, right? This is code that we know is dense in information, and we can use the other techniques on it, like the word count, for example. So if we run a word count on the outcome of the filter, we get something that could be interesting. In this particular case, we see that C setting is present all the time, and if as well, it means like we keep testing this C setting, and indeed, if we look at those usages, we see that we're testing a type versus the various type in the C setting. So we know at a glance what the function is about, at least the structure of the function, what it's about. If you want to do that with an online tool, you also have one that does just that on Fluent C++. So fluentc.com/control-flow filter. And last technique of the speed reading and last technique of today is to scan for the main action. You probably heard about the 80-20 rule, which means that in general, 80% of the consequences can be explained by 20% of the causes. I think I got it right. I often get it wrong, but I think that was about right. It means that most of the consequences are due to a very small set of causes, and we use this 80-20 rule in performance analysis, where in general in programming, where we have this hypothesis that 80% of the execution time is spent in 20% of the code. I think I got it right. Which means that we want to focus on those 20% to make performance improvements and not on everywhere. And some even say that it's more like a 90-10 rule. Anyway, that's the idea. And I think that we can apply that to the meaning of the code, which means that most of the meaning of the code is located in a small subpart of the code, right? I don't know if it's an 80-20 or 90-10, but I'm pretty sure, I mean, I've observed that time and again. Most of the meaning of the code is located in just a few lines. So this technique consists in scanning and looking for the main action being lines where the meaning is condensed. What matters is speed, right, over accuracy, which means that if we get one line wrong, thinking it's not the main action it is, or thinking it's the main action it's not, then that's okay, because the second pass is always possible. This is to get a general idea anyway. And for a given line, to decide whether or not it's the main action, well, things that are typically not the main action are intermediary variables, or special cases, or error cases. I mean, error cases are very important to get right, but when you read code and you want to know what the code is about, you want to focus on the happy path. And complex thing, I mean, in all likelihood, it's not important, because if it's like 80% or 90% of the code that's not important, then any given line is probably not important. So anything that looks really complicated, we just move on. And there are probably other things as well. Just to get the hang of that, we're going to apply the 4 techniques of speed reading on one piece of code to try and understand it as much as we can without knowing anything about the project. So again, this comes from some open source project on the internet. This is a function, right? We want to know what it's about. let's apply the first technique. Let's apply the first technique by looking at the end. So if you look down at the bottom, we have stud sort, which is C++ to the C++ function to sort. And we saw a collection that's called positions. You can ignore the beginning and end. It's just sorting a collection that's called positions. So positions must be something important. The line before it, we also see positions appear down at the end. This stud transform function applies a function. It applies a function which is called getFirst, which is at the end of the line. Stud transform applies getFirst on every element of insertion map and produces the results in positions. So positions really sounds like something important, and insertion map as well. And indeed, if we have a quick look at the line before, we can see positions and insertion map or insertion something appear quite often. So those must be important concepts in a function. Let's apply the second technique, which was counting words. So we launch a word count, and we do see that insertion map and positions are in the top ranking words, knowing that the list goes down a long way, which confirms our first impression. But there are words that appear even more, like CHR. CHR appears 10 times, but we haven't seen it. We haven't seen it at the end of the function. Let's highlight it. Indeed, it's at the beginning, which suggests that the beginning of the function is about something. It has one responsibility, and the end, the second half, has another responsibility. But we're starting to get some idea on the structure of the function. And if we look at the last line where CHR is used, about middle of the function, we can see that positions is initialized here, and it's initialized from CHR. Right, so those are the important concept of the function, and this is where they connect. So the first half of the function is probably about using CHR or computing CHR, but if we look at the prototype, we see that CHR is const, so it's about using CHR. And the second half is to start with position and somehow enrich positions based on that. Right, now the third technique was about filtering and control flow. So I'm going to remove all the lines that are not control flow and just leave the if and fors and so on. So we see the structure with some ifs at the beginning that look like they, I mean, it's C++, but if I translate that, it means that we've looked for something and we haven't found it, right? So those look like error cases. And then we have a for loop that has a complex structure because it has an if, which has a for, which itself has an if, right? So this looks like where the action is happening. There's a complex structure after some error cases or some preparation. And last technique is to determine where the main action is, right? So the main action is, you know what? Let's go over that code line by line. So I would love to ask you what you think about each line, but since we're not in the same room, I'm going to do that myself, and you will have to agree or to silently disagree.
Yeah, I'll show Jonathan we won't have much time left to do it, so maybe.
Okay, right. So we're going to skip that then. The purpose of this exercise was to see that most of the meaning was located in just a few lines. Okay, let's wrap up then. So if we sum up, we have seen 4 techniques in the code speed reading. We have start reading from the outputs, find the frequent words, filter and control flow, and scan for the main action. Now, those are the 2 parts of those 7 techniques, which all combine. Sum up to all of these. Maybe you want to take a screenshot for reference if you'd like to go back to those techniques later. And if you'd like to read more about understanding code and working with legacy code in general, with this we've covered about 1 or 2 chapters of the legacy code programmer's toolbox, which has a lot of techniques to work with legacy code on a day-to-day basis and be both efficient and happy with legacy code. Thank you.